So, let us continue with our study of proof mechanisms in first order logic. So far what we have seen is proof by using generalized modus ponens, which was different from propositional modus ponens in the sense that we had to unify the left hand side of the rules in order to derive the right hand side of the rules. So, we are going to study resolution refutation proofs, which is a complete proof procedure for first order logic. But first we must understand that what is the completeness issue for modus ponens. So, for that let us look at this example. We have for all x px implies qx, right. We also have for all x not px implies rx, right. Then we have for all x qx implies sx and for all x rx implies sx. Now, we should be able to conclude SA from this. Why? Because it is either PA or not PA, right. It is either PA or not PA. So, therefore, it is QA or RA, right. If it is QA, then also we have SA. If it is RA, then also we have SA, right. So, we should be able to deduce SA from this, but we cannot do it by generalized modus ponens, because modus ponens will not observe that this and this, the left hand sides together, cover the entire domain of the predicate, because it is either Px or not Px, right. That this and this together gives us true, the OR of these is not observed by generalized modus ponens, right. And the problem is that this kind of thing, that where you have not Px implies Rx, cannot be converted to Horn form, because we have negation on the left hand side, right. What is the problem of having negation on the left hand side? Now, recall that the basic way in which we were attempting to do the proofs was start with the what we have in the knowledge base. From that we try to deduce new and new things, right. Now, whatever you do not have at this moment in the knowledge base, you cannot say that it is false, right. You cannot say that it is false, because so far you may not have it in the knowledge base, but through the deduction procedure it may come into the knowledge base, you may be able to deduce that into the knowledge base, right. So, therefore, a priori you can never say that not of Px or not of PA is true, because at this point PA may not be there in the knowledge base, but through deduction we may be able to find PA and put it in the knowledge base, right. And you could say not PA when after your entire forward chaining is over, you have deduced whatever you could, and in spite of that you are not able to deduce PA, then you can say that okay, I am not able to infer PA from what knowledge I have, right. But deduction of not PA was not possible there. So, therefore, if you have not of some predicate on the left hand side, then the mechanism of unification that we talked about is not going to work, because we will never have a predicate, we will never have a state of the knowledge base where it contains not of P something, right. This is the problem that we have in modus ponens. Now, is it clear what I mean to say? Okay. In the knowledge base, what we are maintaining is, we are maintaining the set of facts that we have been able to deduce, right. So, if we have been able to deduce PA, we will put it in the knowledge base, right. But how do we deduce not of something, right. So, we do not have a mechanism of storing the knot of something in the knowledge base. So, what we find is whatever truths that we have in the knowledge base, we use that to deduce new things. Now, here we have this rule which says knot of p x implies r x. So, when can we apply this rule? When the knowledge base gives us knot of p x, but if we go by the modus ponens kind of inferencing, then the knowledge base will never tell us knot of p x, because if p a is not there in the knowledge base right now, it is not able to say that not p a is true, because p a could be coming into the knowledge base as a result of the deduction, right. So, being able to infer knot of p a and then use this rule knot of p x implies r x will not work, right, because the only way of doing reasoning there was to take the left hand sides of the rules and try to unify them with what we have in the knowledge base and then deduce the right hand side from that, and we did not have negation here. The moment we have negation on the left hand side, this procedure will not work anymore. Then the knowledge base can become non-monotonic, in the sense that if you insert knot of something at some point of time, later on you deduce that fact, then you have to take out this knot, and not only do you have to take out this knot, you have to take out whatever was deduced from this knot, right, and that makes things quite complex. But there are actually knowledge bases which use non-monotonic reasoning, and they do maintain the consistency of the knowledge base as the deduction procedure continues. But as of now, if we just use modus ponens, we have this problem. So, this tells us that modus ponens is an incomplete reasoning procedure. It is not able to deduce whatever that can be deduced. So, for example, here SA can be deduced, which we know from reasoning, from human reasoning, we know that SA can be deduced, but we cannot deduce it with modus ponens. So, it is an incomplete procedure. So, there was a lot of research on the completeness of a proof procedure, and then Gödel's completeness theorem partially solved this matter. It said, for first order logic, any sentence that is entailed by another set of sentences can be proved from that set. So, in other words, what this says is that if there is any sentence that you can deduce from a given set of sentences, then we will have a proof procedure that is able to do this deduction. In other words, the problem of deduction, or to find out whether it is entailed, whether it can be deduced, is solvable. This is what Gödel said. But he did not suggest a proof procedure, and in 1965 Robinson published his resolution algorithm, which was proved to be the complete proof procedure for first order logic. But there is a catch in the whole thing. This entailment in first order logic is semi decidable. So, what does this mean? It means that we can show that sentences follow from premises if they do, but we cannot always show if they do not. So, let us understand what this means. Suppose there is some sentence that we want to deduce, right. Now, if it is the case that what we have in the knowledge base implies this particular sentence, then we will be able to deduce it, right. But if it is not implied, then we may not terminate. And that applies to all proof procedures of first order logic. So, that was what was the outcome of these two results, Gödel's completeness theorem and Robinson's resolution algorithm. So, when we say that the resolution algorithm is complete, it means that whatever can be deduced will be deduced by the algorithm, but whatever is not implied or whatever is not entailed from the set of facts and sentences that you have in your knowledge base, whatever cannot be entailed, for those cases the algorithm may not terminate, right, and there is no algorithm which can guarantee both. There is no algorithm which can guarantee both the yes answer and the no answer. Can be deduced yes, cannot be deduced no, right. Both of these answers cannot be guaranteed by any algorithm. That is the hardness of the problem itself. Okay. That is why we say that entailment in first order logic is semi decidable. It is decidable on one side, it is not decidable on the other side. Right. We will not go into the details of the validity problem of first order logic, but we will just get a glimpse or try to see why this becomes so difficult, right. So, with this example I will show you why this becomes difficult, but I also encourage you to study Church's proof of the fact that the validity problem of the first order predicate calculus is partially solvable. This proof is available in several books, including Russell Norvig and Johar Manna's book. So, you should at some point of time have a look at how this proof looks like. It is not a very big proof, but it requires a little bit of breaking your head into. Right. Now, let us see this formula. What we have here is a conjunction of predicates P, each having a different argument. So, we have P F1A G1A and P F2A G2A, right. So, let me expand it out and write. So, this has P F1 A G1A and P F2A G2A, and like this up to P Fna Gna, right, and we have for all x, for all y, P of xy implies P of F1x G1x and P of F2x G2x and then this whole thing from here to here implies there exists Z Now, let us see what this says. It says that this is a starting point. We are given a value A. This A is a constant. This A is a constant. Actually, I should have written it in capital letters. This A is a constant. So, we are given that P of F1A G1A is true, P of F2A G2A is true, and so on, and P of Fna Gna is true, right. Okay. And we are given this rule which says that for all x for all y, if P of xy is true, then we have P of f1x g1x is true, and P of f2x g2x is true, and so on, P of fnx gnx is true, right. And then we say that if this whole thing is given to us, can we deduce that there exists some z where the arguments of P will become equal, right. Now, let us see how would forward chaining work. It will start with the knowledge base having P, having this part. It will have P of f1a g1a, it will have P f2a g2a, and it will have P fna gna. Right. This is what the knowledge base will have, right. And then you will repeatedly use this rule, because you will take each of these P x y and then you will deduce this whole set of statements from that, right. So, when you take say P f1a g1a, then x will be instantiated with f1a, y will be instantiated with g1a, and then you will have P of f1 of f1a, g1 of f1a, right, and so on. You will generate this whole stuff, right. Again you will use that repeatedly, but whether these functions will eventually, by repeated application of these functions, whether these two functions will take you to a common value z is the question that we have to answer, right. Now, these functions can be arbitrarily complex functions, right, and to determine whether they will actually converge to a common value is a difficult problem, and this is where the unsatisfiability will creep in, because see this can keep on growing and without you being able to infer whether they will arrive at a common value, right. So, actually the proof which tries to establish that this is partially solvable starts with a formula like this and then develops it to lead you to the proof that you will not be able to, if you are able to deduce this, if you are able to find the z, then you are done, and if you progressively systematically expand these, then if there is a z you will find it, because you can recursively start enumerating this, the values for which this P holds, right. You can recursively start enumerating that. So, if there exists a z, then eventually you will find it, but if there does not exist a z, you will keep on applying this repeatedly and you will not converge, you will not terminate, right. So, I am not going into the detailed proof in the class, but please study that. So, here is the generalized resolution rule. So, let us study this closely. We are given say two rules which has P1 through Pn1, it implies R1 through Rn2, and we have S1 through Sn3 which gives us Q1 through Qn4. And for some j and for some k, we have unify Pj Qk is theta. So, it means that one of these, this Pj out here and this Qk out here, they unify, and they unify under the substitution theta, right. Now, do you see what we have here? We have this Qk here and this Pj here, and they unify with substitution theta. If they do, then we can deduce P1 through Pj minus 1, so excluding this Pj, and Pj plus 1 through Pn1, right, and this S1 through Sn3, this whole thing together will imply R1 through Rn2, and on this side, oops, I have missed out the Q1 here. It is Q1 through Qk minus 1 or Qk plus 1 to Qn4. There is a Q1 here which I missed out. Now, try to see how do we get this. How do we get this? Okay, let me rewrite this stuff. The first one, which tells us P1 through Pj Pn1 implies R1 or Rn2, right. So, we can remove the implication and write this as not of P1 or not of P2 or not of Pj, right, or not of Pn1 implies, sorry, we have eliminated the implication. So, not of this thing or R1 or R of N2, right. This is the first one. So, this 1 to this 1 dash, same thing, but we have written it without by eliminating the implication. Recall that we eliminate implication by writing A implies B is not A or B, which is equivalent to not A or B. That is how we got this, right. Then likewise, if you look at the second one, we have S1. So, we will have not of S1 or dot 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 or not of Sn3, right, or Q1 this is the second statement, and we are given that our Pj here. So, we have unify the Pj here, this Pj, it unifies with Qk, this Qk with the substitution theta, right. Then if these two become the same, if this Pj, mind you, not it is Pj which unifies, not Pj, right. Then when these two under the substitution, these two will become the same, under the substitution theta, this will become the same. So, if they become the same, then either this is true or this is true, because we have not here. So, if we call this say j, then this is either j is true or not j is true. So, it is either of these two which is true, right. So, if either of these two is true, yes, then we can say that the OR of this whole thing is true, right. So, we can deduce the OR of this whole thing, right. And when you take the OR of this whole thing and again turn it back into implicational form. So, if you take the OR of this whole thing, what are we going to have? We are going to have not of P1 or not of P2 or not of Pj minus 1 or not of Pj plus 1 right, dot 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 not of P n1, and then if we take these knots, then we will have not of S1 through not of Sn3, right. Then with this OR of, we have the R1 through Rn2, right, and we have with that Q1 through Qk minus 1 or Qk plus 1, okay, or dot 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 Qn4. How did we arrive at this? We observed that this, if we take this and this, then either this is true or this is true. So, actually what do we have? We have this whole thing and this of whole thing, and if you have one literal which is the complement of the other, then it becomes the OR of the whole thing, right. So, we are able to get this stuff. Now, if we translate this back into implicational form, then we will have P1 through Pj minus 1 conjunction of them, right, and then Pj plus 1 through Pn1 and S1 through Sn3 will imply this whole thing will go to the left hand side of the implication, this OR will become the implication, and we will have this conjunction, the disjunction of these things. So, that is what we have out here in the out here, that we have P1 through Pj minus 1 and then Pj plus 1 through Pn1 and S1 through S, right. Clear? So, this is the generalized resolution rule, and I will ask you to verify that this rule will encompass all the rules that we have seen so far. I mean, all the rules in the sense that it will also encompass modus ponens that we have seen, right. Now, let us see our earlier example and see whether it is solved by this. Now, do you remember the example that we had, or let me write it down once again. Wait. Yes, we had this example. We had for all x Px implies Qx, and for all x not Px implies Rx. Then we had for all x Qx implies Sx, and for all Rx, for all x Rx implies Sx, right. We will use this now here. So, we start with Pw implies Qw and Qy implies Sy, right. Now, here we have the substitution of y being replaced by w to give us Pw implies Sw. This is simple modus ponens, there is no resolution rule being applied here, right. Then when we come here, this is where we find slightly different thing. This is a sentence, this true implies Px or Rx is a sentence which you cannot express in Horn logic, because you have OR on this side, right. But we can always express that for resolution. So, you have true implies Px or Rx, which says that either Px or Rx must be true every time. If we substitute w by x, then we have Px implies Sx, and therefore, we have true implies Sx or Rx. Then we have Rz implies Sz, and again if we use A in place of x and Z A in place of Z, then this becomes RA implies SA, right, and this becomes true implies SA or RA, right. So, that gives us true implies SA or SA, which is SA. So, the difference that we had with modus ponens was that we were not being able to use rules of this form in modus ponens, and we are now being able to use them, right. Okay. Is this clear? Any questions? Right. Now, how do we do this thing in an automated way? So, we will allow the user to write the formulas in first order logic using the normal constructs of first order logic in any way, and then we will try to reduce the formula into a canonical form, into a form from which resolution will be able to work. Now, what kinds of canonical forms do you have for normal satisfiability? CNF, conjunctive normal form, disjunctive normal form, right. So, these are standard normal forms into which you can reduce a Boolean function. There are other canonical representations like binary decision diagrams. So, for this we will also convert to something which is called a clause form, and clause form is like CNF, where you have a conjunction of clauses and each clause is a disjunction of literals. That is what we mean by conjunctive normal form in propositional logic. So, here we have these quantifiers. So, we have to find out some mechanism of getting rid of the quantifiers before we can apply those kinds of strategies. So, the first step, okay, so this is the definition of the clause form, where we will have only universal quantifiers followed by a conjunction of clauses. Each of these clauses can be a disjunction of some predicates, right. All first order logic formulas can be converted to clause form, and we will demonstrate this conversion on this formula. Okay. We will demonstrate the conversion on this formula. Now, follow the steps closely. Step 1, we will take the existential closure and eliminate redundant quantifiers. So, if there is any quantifier which is redundant, that will be eliminated, and we will take the existential closure of those variables which are not quantified. So, for example, here we have this there exists z, but there is no z here. There is no z in the formula, we have this there exists z. So, this there exists z can be safely dropped, right. This is the elimination of a redundant quantifier. Also, here we have this x1 and there is no quantifier on x1. So, in the absence of the quantifier, we will put a existential quantifier here. We will see whether there exists some x1 for which this whole thing holds, right. That is step 1, clear. Step 2, rename any variable that is quantified more than once. This y has been quantified more than once. See, we have this for all y here, we have this for all y here. Now, this y and this y need not have the same value. because they are separately quantified. If this for all y was not there, then these y's would be the same y, because they would come under the scope of the same quantifier, right, because they are under different quantifiers. So, therefore, these two y's are different. So, we will rename one of them. So, we will rename this y to z, and here we will have for all z qxz implies px, clear. So, any quantifier, any variable which is quantified more than once, for that we will just give it a new name. If you change the name of the variable, it does not change anything as long as it is quantified. Okay. Step 3, we will eliminate implication. This is straightforward, we know how to do that. So, this implication is eliminated by not of px or this whole thing, right, not a or b. Step 4, move the negation all the way inwards. We will move this negation all the way inwards. So, here this negation was not directly on the predicates, this negation was on this whole formula, on this sub formula. So, we will move it inwards. So, by moving it inwards, we have this there exists y, for all y becomes there exists y, and we have qxy and not of pfx1, right. So, this not has been moved inwards, right. Step 5, push the quantifiers to the right. So, here this there exists y was quantifying this whole formula, but then this part, this not of pfx1 does not have y. So, we can associate this there exists y directly with this predicate qxy. So, that is what we mean, we move it inside and align it with the predicates which they are quantifying. So, it is here there exists y qxy. Likewise, this for all z is not quantifying this px because it does not have z. So, we have moved it inwards, right. Then this is an important step. Eliminate the existential quantifiers using skolemization. So, we had briefly seen what we mean by skolemization. We replace an existentially quantified variable by some ground thing, by some ground term or something else in order to get rid of the existential quantifier, but we can do it with only something which is not there in the knowledge base at the moment. So, what we do is we pick out the leftmost there exists y by and replace it with b of some x1 through xi1 through xin, where these are all the free variables of there exists by that are universally quantified to the left of there exists y by, right. Now, let me explain this through an example. Let suppose we have there exists y by, right, and you have some for all x1, for all x2, for all x3 here, right. Now, see what does this say, that for all x1, for all x2, for all x3 there exists xy, there exists such a y. So, given a value of x1, x2 and x3, there will be a y which satisfies by. This is not the same as writing there exists y for all x1, for all x2, for all x3 by. What is the difference between these two? In the first one, there has to be a single value of y for which no matter what is the value of x1, x2 and x3, by will be satisfied, right. But here it says that for all values of x1, x2 and x3, for each of those combinations of x1, x2, x3, there has to be some y. So, if x1 is a, x2 is b and x3 is c, then we can have one y. If x1 is p, x2 is q and x3 is r, then we can have another y. Those two y's need not be the same y, right. So, therefore, when we replace this y with this column, we will replace this by a function of x1, x2, x3. So, given the value of x1, x2, x3, y is that value which satisfies by. Now, the value of y which satisfies by for this x1, x2 and x3 is a function of these three. So, we can have a mapping from triplets of x1, x2, x3 to the value of y which satisfies by. For a different value of x1, x2 and x3, you will get a different y, possibly a different y, right. So, is this clear what we mean by Skolemization, right. So, yes. Here no, because it is a function. So, for any given value of x1, x2, x3, there will be a y. There can be more than one y, like we had, you remember that there exists x likes x ice cream and we replace x by man. There can be more than one x who likes ice cream, but man is one which satisfies it, right. There could be others also. Similarly, we are interested in finding out whether there exists any such y. So, if you are able to find out a function which gives you one y for every combination of x1, x2, x3, then this formula is valid, right. So, it is a question of the question is whether such a function exists. That is what is going to determine whether this whole formula is valid or not. If it is valid, provided that there is a function like this which gives for every value of x1, x2 and x3 a value of y which satisfies by. But I agree that there can be other y's which will satisfy by. So, what we have here is we eliminate the existential quantifiers. Slides please. We have these existential quantifiers. So, this is the formally we write it down, that pick out the leftmost there exists y by and replace it by this b of x1 f of x1 through xn, where this xi1 through xin are the free variables of by that are universally quantified to the left of there exists y by, right. Now, one thing that none of you asked me here was text please, text please, text please. Yes, we had none of you asked us that look this y, if this predicate does not have x1, x2, x3, then how does it matter? I mean, why does it have to be a function of this x1, x2, x3? So, in this case we do not need this, we need this when you have here also okay. Then Skolemization of this whole thing is going to give us b of right. These x1, x2, x3 could be in the same predicate, or it could be it could also be a collection of predicates. For example, this b could be a formula of the form say b y x1, right, and then some say B1 and B2 x1 x2 and B3 x2 x3. See, even in this case, though they do not appear in the same predicate, but there is a binding which is there like this. So, therefore, this y, if you have for all x1 through x3 here and you have there exists y, then to scholemize this y you will have to put function of x1 x2 x3, right, because though you do not have x1 x2 x3 all in this formula, in this predicate, there is a binding which has this. So, this whole thing is our B, right. Fine. So, this x1 through xi1 through xin are all the distinct free variables of there exists y bi that are universally quantified to the left of there exists y bi. So, in this case, for example, in our example, we have this there exists y qxy and we replace that this y by gx. Why? Because this x is universally quantified here. So, the value of y that we have here has to be a function of that x, because the there exists y is inside this for all x. So, given the value of x, the value of y will be a function of that x. So, we have this gx. This is the Skolem function. We call this the Skolem function. For the x1, there is no such requirement, because there is no other variable in this predicate which is universally quantified from the outside. So, we simply replace it by constant a, which does not appear anywhere in the knowledge base, right. Also, this function g that you have here has to be a new constant, new function constant. It should not be one of the existing ones in the knowledge base, right. Finally, we move all universal quantifiers to the left. Now, we do not have any existential quantifiers. So, we can move the universal quantifiers to the left. Previously, we could not do this because the existential quantifiers were there and you cannot move a universal quantifier across an existential quantifier, right. But here now we do not have any problem. So, we have moved it to the left. So, this for all z has come to the left. So, on the right side we now have just a set of predicates which are quantified from the outside. And now, what we are going to do is we will distribute AND over OR to bring it to clause form. See, up to this part is what is mainly the jugglery with first order logic that we have to do. Once you have all the quantifiers to the left side and they are all universal quantifiers, what you have on the right side is like a set of predicates, right, which are quantified from the outside. So, we can use our Boolean algebra on these to convert this stuff into our CNF form. So, that is what we do here. So, we have distributed the AND over OR, and that gives us a set of 3 clauses. One is not Px or Qx Gx, the second clause is not Px or not of PFA, third clause is this, right. And then we simplify this. This is an optional step to obtain this not of Px or Qx Gx as one clause and not of PFA as the other clause. How do we get this from this? Try to solve it. Take this down as an exercise and just try to see how we deduce this thing from this. It's not difficult. It's just to give you an idea of. It will give you an idea of how to use unification in order to get rid of the third clause. Okay. So, in the next lecture we will see how we can use resolution refutation with some examples to deduce or to prove certain sentences in first order logic. Yes, the slide please. Thank you. Okay. Just to we come to the end of this lecture here. So, we will continue with our analysis of first order logic, and today we will study a kind of proof mechanism called resolution refutation proofs. So, today's lecture will be on resolution refutation proofs. The basic idea of resolution refutation is as follows. We will first convert the set of rules and facts into clause form, and recall that in the last class we had discussed that a clause form is a conjunction of clauses, and each of these clauses can be a disjunction of predicates or their negations. So, that is the clause form. In the clause form we have only the universal quantifiers, and all of those universal quantifiers are pushed to the left. So, any variable that we have in the clause form is universally quantified from the outside, right. For the existential quantifiers, recall that we used a thing called skolemization to replace the existentially quantified variable by skolem functions. So, after converting the set of rules and facts into clause form, we insert the negation of the goal as another clause, and we try use resolution to deduce a refutation. So, let us see what I think we had discussed this in the context of propositional logic. The idea is that if I have a set of clauses C1 and C2 and some Ck, suppose this is the set of k clauses that are given to us, and we want to deduce whether this implies the goal, right. So, then if this has to be valid, then the negation, then it is equivalent to writing not of this C1 and Ck or G is valid, right, or the negation of this, which means C1 Ck and not of G is, if this is valid, then the negation of this is unsatisfiable. Okay. So, if we can deduce that this thing is conflicting, in the sense that from this if we are able to deduce false, that means that this set of clauses will be inconsistent and therefore unsatisfiable, and therefore this original thing that we wanted to prove will be proved, right. So, if we use resolution to deduce refutation, then if a refutation is obtained, then the goal can be deduced from the set of facts and rules. But recall that because of the semi decidability of first order logic, it may also be possible that we continue forever and we are not able to deduce false, right, and that resolution continues forever. and that will happen for the kind of formulas that I had shown you previously, that which has functions within the predicates, and there is a recursion in the function which never terminates. So, in the last class we had studied the conversion to normal form, where we had seen a set of steps that converts any given formula to normal form. So, like taking the existential closure and eliminating redundant quantifiers, then renaming any variable that is quantified more than once, eliminating implication, then moving negation all the way inwards to the predicates, pushing the quantifiers to the right, then eliminating existential quantifiers as I was mentioning through a Skolem function, which is also called Skolemization, followed by moving all universal quantifiers to the left, and finally distributing the AND over OR to get the conjunctive normal form, and finally an optional step to simplify, so that in the end we get a set of clauses. So, here for example, this not Px or Qx Gx is one clause and not of Pfa is another clause. Let us quickly see whether the example that we have done can be derived using linear resolution. Actually, this particular case can be derived using input resolution also, but in general input resolution is not complete, but linear resolution is complete. Please take some time to think about why linear resolution is complete, but input resolution is not. So, this simple generalization which allows us to use the ancestor clauses in the proof tree makes the resolution procedure complete. So, how will you show that it is complete? Take any resolution proof and try to convert it into an equivalent linear resolution proof. If you are able to do that, then that means that linear resolution is complete.